Welcome to this morning's inspection debate, taking the next steps in line optimization. Inspection systems are the eyes and ears on the line, and they're evolving with the smart factory debate. So this panel here today is going to discuss some of the next steps in technology that are going to help us optimize the line. I'm joined to my far right by Joel Scutchfield from Co-Young. To my right here I have Alex Malik from Saki. To my left we have Brian D'Amico from Murtec, and on my extreme left we have Keith Bryant from Exelon International. So welcome, gentlemen, and thank you for joining us today.
Thank you for having us.
Okay, no worries. Good.
Thank you for your invitation.
Good. So I'm going to kick off with my very first question. We'll start with you, Joel. We currently have many SPI systems in the market that can feed rudimentary information back to the printer. What other information will these systems be able to provide in the future?
Sure. No, you're absolutely right, Trevor. So things like X shift, Y shift, theta, clean cycle, that's been around for a while now, right? And we're able to do that with all of the usual suspects on the printer side. What we've been focused on over the last couple of years is really taking that to the next level. So starting with being able to advise the setup operator on the proper settings for speed, pressure, and release by utilizing an automated design of experiments tool, which provides that information based on the information it's collecting over a 10 to 12 piece run. Once we have that information in place, we now have a tool that will also be able to monitor to a much greater degree things beyond X shift, Y shift,
Right.
trending in volume, in presence, absence, and automatically give the operator information on what's going on and what the possible causes of those issues would be, and then what to do about it, where to look to find the corrective action quickly. So that's certainly something that we, and I know others, are working on. And the final piece to that is actually using the artificial intelligence element and machine learning to actually take complete control of the printer for those particular settings. Right. And there certainly is that group of customers out there with a very global presence that have labor challenges in certain areas that are very interested in that.
Yeah, I mean, it certainly is a challenge. There's so many different parameters to try and get artificial intelligence making these decisions. I think it's assisted intelligence we've got now as opposed to artificial.
Right.
Alex, what is your view on this? I mean, there's lots of areas that we need to be able to advise on, squeegee pressure and different things like this. Where do you see it going in the future with SPI?
Actually, we have a similar approach. What we think is the most important element, it is critical to talk from SPI to the printer, and of course the screen printing is the most important step of the PCB assembly because that's the whole foundation of the PCB assembly. But we are also looking at the next steps, and at Saki, since we have the SPI and AOI and X-ray, we start with volumetric measurement of the solder paste. And then with the capability that we have, and most of our customers, they have 4 of the inspection machines in their processes: SPI, AOI pre-reflow and AOI post-reflow, as well as X-ray. We would like to capture, based on the volumetric measurements of the solder paste from the beginning versus at the X-ray, and for us to completely understand if there are any variations and really what happens to that solder paste, including capturing all that data throughout the whole process. Okay. So we think it's an end-to-end complete solution, including the machine learning and artificial intelligence and all that, versus just from SPI to AOI. Yeah. We look at the whole picture.
Yeah, you're right. I mean, there is definitely a trend towards having a more holistic view of the entire inspection process. I mean, Brian, you have something similar as you were demonstrating last week with the smart loop system. Can you talk a bit about that?
Yeah, sure. First of all, I agree with what the gentlemen are saying as well. The goal along the way here is to collect a lot of data, collect what's called big data. Okay, so once we collect the big data, we can actually determine if there's perhaps less solder on a pad. Okay, we can monitor what the settings were on the screen printer that resulted in that issue. And if you see enough of a trend and you see enough of something to tell you exactly where the process occurred, where it broke down, once we collect that big data, we can then take and make predictions as to how to set up the screen printer in order to avoid those defects in the future. So if we found that the squeegee pressure perhaps was a little bit too much, and it was scooping the solder paste out, resulting in less volume, then we would know that just based on the big data that we've collected. We know that once we have this setting set up in this manner, we end up with less solder volume. Then that would be like instructions back to, we don't want to control the screen printer. I think that's going to be a bit of an issue with many people, quite frankly. But we do want to provide a level of information back that somebody could take action on. What Keith is probably going to talk about, I think it's very important, is the screen printer is basically a dumb animal, right? So I think that the best thing to do is to add some intelligence to the screen printer, which would allow it then to take the data that we're providing back and make that actionable data. And I'm going to let him talk about that because, quite frankly, he's got some pretty neat stuff to talk about on that.
I know you were talking about it off camera, and I think you made a very pertinent point. So perhaps you could tell us what your views on this, Keith.
Yeah, I mean, it's quite a simple one, and it depends on which experts you talk to. But if you talk to process experts, somewhere between 50 and 85% of the faults that affect yield come from the printing process. And we talk about data. To get data, you need sensors, you need feedback. The more data you have, the more, the more of an informed or simply an accurate decision you can make. And quite simply today, the printer is the dumbest thing on the production line. Yeah, you've got squeegee pressure, you've got squeegee speed, you've got snap off, and pretty much that's about it.
Right.
But if you look at the potential, you look at one failure, insufficient paste on the board that the SPI finds. It can be insufficient paste on the stencil, the paste can be too dry, the apertures can be blocked, the rheology of the paste can be gone so it's not rolling properly. Braining gear. Coplanarity, the relationship between the two, the gasketing of the board, all of these things affect whether you're going to get a good print or whether you're going to get insufficient. And at the moment, all of these guys are brilliant at spotting insufficient. But what we don't know is really what's causing it. If it's outside of squeegee speed, it's outside of squeegee pressure, there's not really much we can do because we don't have the data.
Right.
And the whole thing about 4.0 smart factories is doing intelligent stuff with the data. And as Brian said, big data is the thing that everybody's talking about. And at the moment, coming out of the printer, which is acknowledged to be the bad guy in the process, we're getting the smallest amount of data.
Right. Now, you're absolutely right, and I think the having sensors on the paste to measure the rheology of the paste makes a lot of sense because of the. You said 50% defects coming out. Some people say as high as 70.
Yeah, I mean, some people say 85.
Right, but of the largest number of these defects that coming off are insufficient paste. So there has to be some system coming in. So maybe what you're suggesting is it needs to be more communication coming out of the printer to go into the SPI systems.
I mean, I've talked to a few of the guys, and it's simple stuff. I mean, weigh the stencil. Weigh the empty stencil, and then weigh it every so often, and the difference is the weight of the paste. Put a piezoelectric crystal in every corner of the mount for your stencil. You won't only know squeegee pressure, but you'll know whether the pressure is even. You'll know how fast it's moving. You'll know if there's any juddering or whatever in the mechanics of the system. And, these are all peanut stuff that's elsewhere in a lot of the things in general industry that cost a few bucks.
Yeah, definitely. I agree.
It was exciting.
It is exciting. I'm losing my place here. Okay, so missing paste. As we were talking there, Joel, it's the single biggest defect emanating from the printer, and many manufacturers are putting dispensers after the printer to make up for the missing paste to correct these deficiencies. So will future SPI systems also communicate with these dispensers?
Yeah, that's certainly something that's in the works as well, right? We have such a tool, so naturally we want to be thinking in those terms. It's been interesting this week because with that repair tool, we've actually, I guess, elicited ideas on other applications beyond just filling the void that was left from the print process. But certainly, as far as the closed loop side of things goes, that's the next piece on the horizon, right? So, yeah, it's an evolutionary process, right? It's gonna continue to grow.
Yes, so absolutely. We understand that Koyoung and Parmy are adding a dispenser to their SPI process. And of course, this will address some of the missing solder paste placement. But my approach is different, is totally different. And this is also based on the feedback that we have received from our major EMS customers. And the approach is that, as we, 4 of us, 5 of us agree, is that screen printers are the issue. Adding a dispenser will band-aid a problem, a process issue, is not a resolution to that process issue. We are adding $30,000, $20,000, depending on the supplier of that, to another piece of equipment, and we are adding another piece of equipment. Now we have to develop software and hardware for the M2M communications between all of these machines. So in my opinion, the industry some of the customers that are desperate, they have to adopt this, but in the long run, this is not a solution to solve this problem. Is a screen printing problem. That process needs to be solved, and in the long run, we don't see a need for having another dispenser on the line.
Well, let me give you another scenario to that. I mean, some people actually talking, one of the issues with the dispensing is it doesn't keep up with line speed. But if you put 2 dispensers in tandem, you can very often keep up with line speed. And with miniaturization coming in, and the increasing need for 3D paste dispensing, is it not going in the direction of eventually we're going to be dispensing rather than printing?
Well, I think the issue there is speed, right? That's the limiting factor. Just to address the point that Alex made, I agree. The ultimate goal is to fix the printer, right? The issue with the dispenser is to prevent from having to wipe clean that some of these customers we're working with are making very expensive products, very large boards, high densities. So it basically gives them an opportunity to continue along with that particular board that's printed. Now we're still capturing that information that says we had an insufficient, and that's again then fed back into the cycle of how do we correct that, right? How do we fix that so that doesn't happen? So we don't have to use the repair tool. Yeah, but to Trevor's point, that is the driver, right? As the packages become smaller, as the need to deposit smaller and smaller amounts of paste and so forth, it's you basically have to have some mechanism to accommodate for that. Yeah.
Now, I just know, talking to some of the paste guys, that they feel it might be heading in that direction.
Well, let me address that.
Okay.
First of all, I don't think we're answering the question that you asked.
Okay.
Quite frankly, the question you asked is, will SPI machines be able to communicate with the dispensers? Mm-hmm. And there is an advent of dispensers being put into place after the screen printer, but it's not so much just to make up for solder that's not there. And let me go into this. All right, first of all, the screen printing process is the most efficient, the best out there, quite frankly, because it's very fast, it's easily controlled, repeatable. You can monitor your paste better, versus leaving, being able to change over paste from RMS to lead to lead free. But the reason why people are putting dispensers after, and I'm talking about a dispenser, not just part of an SPI machine, the reason they're putting dispensers after the screen printers because it's very difficult to have a screen that allow you to screen for 01005s and some larger format, components that will be on the board. So your stencil thickness, you can do step down stencils. That's kind of an issue. So realistically, if you have to either add solder to certain locations on the board, you would use a dispenser. Or what some people are doing is they're printing everything except for the smaller devices, and for those smaller pads, they're using a dispenser. So the dispenser is basically being an augmented means of solder deposition to make up for those things that we simply can't control through one screen.
Right.
So your question was, would we communicate with the dispenser? And the answer is absolutely. Of course, all of our machines are going to provide data, back, not yours, data back as far as, what the SPI sees. That's going to be available to the dispenser, and dispenser can take and use actionable data on that. Right. So as far as the debate whether or not we have to have a dispenser in the SPI machine, I think if the dispenser on an SPI machine was of more value, meaning that it can do things like just place, just go and place dots down on certain locations versus just those that have been determined to be less solder volume, that would be a benefit, and I think that's a sellable item, quite frankly, to manufacturers.
Right. And those are the kind of things that we're hearing this week, right? Yeah, just exactly what you said.
Makes
I'm gonna block these apertures, and we want to dispense in those locations for the reasons that we just discussed. The beauty of having the tool inside the SPI machine is that after you dispense, you can re-inspect, right? So I'm sure completely agree with that. Yeah. But yeah, it's.
There are printers out there that do have dispensers inside them, which do that function. Do you have any input on?
Well, no. I have to say I really like Brian's idea, and more and more when we look at lines, we're seeing lines with printers and dispensers, and they're either going one way or the other. The printer is putting down the small stuff, and the dispenser is adding material where it needs to, so you still have a good amount of solder for the joints where you need for your bigger components, or they're using a thicker stencil and they're doing the big stuff, and they're jet dispensing all the smaller bits.
Right.
But no, my question to Brian is basically, if you go with this plan, then you do a 3D inspection of the solder paste, and then you need to use the dispenser again to fill in the gaps.
No, what I'm talking about is, quite frankly, I'm talking about the dispenser being after the screen printer. If you have a dispenser on the SPI machine, then you can fill in the gaps right at the SPI machine. But
then if you find some areas where the stencil has been blocked or whatever, then you want to just be able to go back in with the dispenser and put paste on that, so you don't have to wash the board off, or in some cases where customers don't allow wash-offs, throw the whole damn thing away. And then afterwards, you want to use the 3D AOI to check to make sure that where you put the stuff, it still works. Right. So I love the theory, but now we need the intelligence to be able to multi-dispense and multi-inspect from the same machine.
All right,
this is easy stuff.
Yeah, but why do you need to have two different technologies there? You've got a stencil printing system, and then you've got a dispensing system. If you had two dispensing systems that were able to keep up, then you get all the benefits of that. In other words, you wouldn't need to wait a day or two to order stencils and all the issues that come with that, and step stencils. If you improve the dispensing technology to be able to keep up with line speed, I think that would be
it's a good
get the program as well.
It's a good theory, but you've still got issues of speed. You've got issues of cost. Not only about the machines, but you're using Type 5 paste with a dispenser. You're using Type 3 when you're printing. Obviously, the rheology of the pastes are different. If you put down too much Type 5 paste into a big area, it's going to slump because the balls are small and there's more liquid attached to it because of the flux. So you don't really want to dispense really big areas. Right. It's ideal to top up, and it's ideal to use for small things. But dispensing is not the best technology for big chunks of solder paste.
Right. Okay. All right. Well, I'll bow to your your wisdom on that.
Yes, I agree with that. And also, my question again would be, how it's going to affect the speed of the line, the throughput of the line, and the cost of two dispensers, and also the maintenance and cleaning of those equipment constantly.
I think the speed and number of heads you're going to get in dispensers will improve over time. But there we go. Anyway, let's move on to my next question, which I'll take back to you, Joel. What are the current limits for inspection equipment in terms of resolution and accuracy? Where are we at?
Well, so for the most part, in the 0105 world, I think we're all very capable, right? So, with a 15 micron resolution, we can take care of that very well, right? When you start to get below that and into certainly more microelectronics type applications, that's where we're starting to see the need 7 micron, 5 micron, or maybe even a separate system altogether to be able to accommodate those kinds of applications. So again, with our standard technology, we're doing very well with the part mix that we're being asked to address today. Once we have this push to go below the 0105, then things change a little bit. Yeah, and we certainly have solutions for that, right? But this kind of seems to be the cutoff point, right?
Right.
So
Right. Okay. Alec.
So this is an excellent question, and frankly a question that we have provided solutions for all of that. In the areas, to Joel's point, in the areas of the 2D AOI, because most companies are using line scanning technology, now we are approaching the ends of the process capability for a loss of components in 2D AOI. Therefore, we are going to the 3D AOI for those smaller components. And also in the 3D AOI, we are getting into the components that, again, our machines we have 18 micron, 12 micron, and 7 micron, and we can capture most of the inspection requirements. And also there are BGAs, QFPNs, and other components that we use our side cameras that can inspect those components. And then also in those areas, in the 3D AOI, we are approaching a limit that most companies or most manufacturers cannot inspect BGA, heading preloads, and other defects. In that area, we have developed our 3XI machines that can inspect and detect all of that. So currently, for 95% of the components out there and in semiconductor industry, we have inspection solutions.
Okay, so that's coming back to that holistic approach you were talking about earlier. Brian, I know you're doing a lot of work in microelectronics as well. You're moving into that area. When you get down to the sort of sub 10 micron level, how hard does it get?
It's not that it really gets any harder, because all you're really doing is... So we've got a 25 megapixel sensor that we use in our camera. We manufacture the cameras, right? That's just the raw sensor itself. What we're dealing with is taking a telecentric lens and then basically gating the resolution, getting the FOV and the resolution of each pixel with a telecentric lens, a precision telecentric lens. For normal SMT, we're talking about 15 micron, 20 micron, 10 micron, that's fine. When you start getting down to 03015s, that's when you require a 7.7 micron or better. We, of course, have semiconductor equipment. We sell a lot to the semiconductor industry. So we've got lenses, same sensor, but we have lenses that'll take us down to 4, 2, and 1 micron. All you're really doing at that point is limiting the FOV, limiting the amount that you're looking for, the region of interest that you're looking for. FOV would be the total field of view, and the parts being the regions of interest within that field of view. So it's just a matter of modifying the lens resolution to meet the application. As you get smaller and smaller, the resolution has to get better and better.
Yeah, makes sense. Can I ask the same question to you, but with a view to X-ray, because that's obviously your area of expertise at the moment. What are the limitations in terms of resolution for X-ray? Where are we at with that?
Well, nothing that challenges us within the SMT area, because effectively our machine is a microscope. We can see features down to 0.1 microns, depending on background, depending on everything else. But one trivia question that I came across a couple of weeks ago. We all know the Hubble telescope. Yeah. Does anybody know how many megapixels is in the lens of the Hubble telescope?
No. It's going to be something ridiculously small.
It's 18 megapixels. Yeah, and when I sit here and I hear you guys talking bigger numbers than that for inline production machines, it just shows really how far technology's gone and how hard you guys are driving the technology.
I think I'm going to call them and sell them a camera. Is what I'm going to do.
Yeah, no, I made a guess at that because it was a number of years that they put that thing up there.
Yeah.
So
But
it makes sense.
When you think about it, it's scary. You've got more on your mobile phone now.
Right.
Camera module on the mobile phone is 18 megapixel.
Yeah.
Okay, let's move on. Next one. Increasingly, robotics are being used to move boards offline for X-ray inspection or rework. Are inspection machines being modified to allow for this semi-automatic function?
If you're talking offline machines, we don't really need a lot of modification to have robotic loading and unloading. It's just a matter of triggering the door. The bigger and better machines have got large doors. The door normally slides open automatically. The robot loads, and as it pulls out, there's either a light gate or something that triggers closing the door. The radiation doesn't start until the door is completely closed and locked, so there's no safety issues from our side. And yeah, in some places we have people who are doing it. The issue that we have at the moment is the way that our systems work. They can do an amount of automated inspection, but the really fine detailed stuff is generally seen by the eye of the operator and the operator manipulating the system.
Right.
So if you have something that's really delicate like wafers that you don't want people handling, then a handling system has some value. Mm-hmm. But at the moment, a handling system for panels in surface mount doesn't really bring much value.
Would you agree with that?
Well, yeah. If the application is conveyorized,
Yeah.
that's the best you're going to get. But for certain applications where you can't, it's not really conveyorized, so we require maybe mixed technology. What we have we actually have our desktop equipment and we have our inline equipment, and we have 3D in both. So quite frankly, we can take and create a program on our desktop, move it over to our inline, vice versa. But if we have a type of application where we're just simply not able to conveyorize that through my inline systems, and actually have a video that we can show you of, this is going to be my desktop unit, and this is actually FANUC. This is their manufacturing facility, and guess what? They're using FANUC robots too. Yep. So this is, we're actually doing a robotic load and unload of their application on our desktop units simply because they're not conveyorized. They cannot be conveyorized.
Yeah.
Can't fit into an inline system.
Yeah.
So for that, the robot puts the thing down, it basically goes into the system, it gets inspected, comes back out, the robot takes, removes it, stacks it if it's good, bad, etc., sorts it. And that's more or less what I think you're talking about when you're talking about robotics being applied to an inspection system.
Absolutely.
Yeah,
Absolutely.
and
we're
I
seeing
can
more
add
of
to
this
that,
type.
Trevor. We with our pin inspection tool. So now we're moving to the back end, right? So again, away from the board level where everything's conveyorized. And I agree with Brian. That's always going to be the best approach. But when you get to back end inspection, which we're hearing a lot about these days, and looking at things like automotive connectors in a vertical format, where now we can basically load that automatically with robotics and then shuttle that fixture, if you will, underneath the inspection head, back out when it's finished, unload by the robot as well. So I think, again, when you start getting into the back end or the non-typical PCB format applications, then that's where you start looking at those kinds of
Okay.
solutions.
So our X-ray machine is both inline and offline. The system that we are currently using is a board stager buffer for the no good boards, and the good ones pass through, the bad boards go through this buffer stager. That's the extent that we have in the robotics of the handling of the defective boards.
Right. Yeah, and I noticed, just to finish off, Keith, I mean, you're trying to push the X-ray system to be a pre-reflow option as opposed to post-reflow option, so that you can capture the defects earlier in the process. Can you tell us a little bit about that idea?
Well, obviously we sell the machines. The customers can pretty much do with them what they want, as long as it doesn't cause any damage. But no, we're seeing a lot more people now looking towards the front of the system. Obviously, the earlier in the process that you find faults, the cheaper it is to fix them, or the easier it is to fix them. And yes, we're seeing people doing, especially for new product introduction. You know, you guys can see a lot of new product introduction, but what the guys are looking at for X-ray is when the components are put down, is the design of the stencil not good? So material is being squeezed between the pads under the components, which is going to cause shorts and solder balls and all of this kind of stuff. So people aren't really using it in production in that way. But you know, when they're trying to set up a capable process, you know, people now are making 5, 6, 7 stencils before they actually go into production. Whereas in the old days, the stencil was 10% of all the apertures, and that was what you started with, and you lived with all the problems. But now, thankfully, the engineers are a lot more aware of how stencil technology can give them much better yields. Yeah. So they're using our machine to check the bits that they can't see, but they're still using your machines to check accuracy of placement and are things moving when they're put down and all of this stuff. So yeah, it's just basically, you know, getting more use from the tools that you have, again, because yield is the most important thing now that everyone is pushing for.
Right. Gentlemen, it's a fascinating subject. We could talk about it all day. There's so many other areas that are affecting test and inspection at the moment. It's a very mobile area. But we're running out of time, unfortunately, so I want to thank you for joining us. Joel Scutchfield from Koyoung, Alex Malik from Saki, Brian D'Amico from Murtec, and of course Keith Bryant from Exelon International.
Thanks.
Okay.
Thanks for having us.
All right, and thank you for joining us today.